In this week, we will discuss one of the most fundamental theorems of complex analysis called Cauchy's theorem. Very broadly speaking, Cauchy's theorem says that if we start off with a domain omega and if gamma 0 and gamma 1 are two curves in omega such that gamma 0 can be continuously deformed to the curve gamma 1, then the integral of f over gamma 0 is the same as the integral of f over gamma 1 if f is a holomorphic function on omega. The notion of continuously deforming a curve gamma 0 to obtain the curve gamma 1 is made precise by the topological notion called homotopy. So let's begin by defining what homotopy of curves is. Homotopy of curves. So let's start with an open set omega in C. Let omega be an open subset of C. And suppose gamma 0, let gamma 0 from say AB into omega and gamma 1 again from AB into omega be curves. Suppose gamma 0 and gamma 1 are having the same initial point and the same terminal point respectively. We then define a notion of homotopy of the two curves with fixed endpoints. So let's write that down. Suppose gamma 0 and gamma 1 have the same initial point. Say z0 and also the same terminal point. Let's call it z1. We then say that gamma 0 is homotopic to gamma 1 with fixed endpoints. Gamma 0 is homotopic to gamma 1 with fixed endpoints. If there exists a continuous map capital H which is from 0 1 cross AB into omega such that the following conditions are satisfied. At stage 0, so this should be thought of as the stage parameter and this is the domain of definition of the curves. I'll explain more on that in a minute. At stage 0, gamma 0 comma t, this is just the initial curve gamma 0 of t and h1 of h1 comma t at the stage 1, this is just gamma 1 of t for all t in AB. And not just that, at every stage the initial point should be z0 and the terminal point should be z1. H of s comma a is equal to z0 and h of s comma b is equal to z1 for all s in 0 comma 1. Let's now see what is the impact of all these conditions that we have just imposed on here on H. So the curve gamma 0, let's draw a few pictures to capture this notion. The domain omega, let it be something like this, and suppose this is our point z0 and this is our point z1, and suppose we have our curve gamma 0 is like this and gamma 1, suppose this is our curve gamma 1. So what do we have? We have a map H. So recall that, let me keep that definition here. There is a map H from 0 1 cross AB to omega. So what we will do is we will think of the first parameter from 0, 1 as the stage at which we are in. So for example, h of s comma t, let this be gamma subscript s of t. So notice that if we think of at the stage s, h of s comma t as gamma s of t, then gamma s just turns out to be a continuous curve from z0 to z1. So let me now use some colors to capture what gamma s will be. So suppose this is what gamma say 1 by 4 is going to be, and then after some further stages, gamma 1 by 2 will be something like this. Very close to 1, this will be something like gamma 0.99 or something like that. So this is how the curves gamma s are captured. So basically this region which I am filling with the blue color, or maybe not the blue color, it's not good, maybe with the dark blue color. So this region which I am now shading by dark blue, that's the region where all the curves gamma s will be, and slowly at every stage. So if you notice at stage 0.001 it will be some curve like this maybe, and it slowly deforms to finally become the curve gamma 1 at stage 1, h of 1 comma t. Notice that h of 1 comma t here, this we have forced it to be gamma 1 at the stage 0, h of 0 comma t is the curve gamma 0. The fact that capital H is a continuous map captures the idea of how the curve gamma 0 continuously deforms to the curve gamma 1. So that's the geometric picture which is being made precise by the definition of H here. Let's now define what is meant by a homotopy of closed curves. Suppose it's not very different. We are just trying to see what happens when both gamma 0 and gamma 1 are closed curves. Suppose gamma 0 is a closed curve at z0, and gamma 1 is a closed curve at say z1. I'm not demanding that the 2 points be the same, they could be closed curves situated at different points. So at z0 means that the initial point of gamma 0 is z0, which is the same as the terminal point of gamma 0. Similarly, gamma 1 is a closed curve at z1 means that the initial point of gamma 1 is the same as the terminal point of gamma 1, namely z1. We say that gamma 0 is homotopic to gamma 1 as closed curves. So remember that the first definition was gamma 0 being homotopic to gamma 1 with fixed endpoints. So maybe I should underline that earlier as well to highlight what was being defined. We defined gamma 0 as homotopic to gamma 1 with fixed endpoints. And now we are defining gamma 0 is homotopic to gamma 1 as closed curves. Again, I didn't define it yet. So if there exists a continuous map H from 0, 1 cross AB into omega. Again, let me go up and show you that both gamma 0 and gamma 1 here are assumed to be defined on the domain AB, the same domain AB. So if there exists a continuous map H from 0, 1 cross AB into omega such that, again, at stage 0, h0 comma t is gamma 0 of t. At stage 1, this is gamma 1 of t for all t in AB. However, at every stage, we are not in a position to demand that the curve be located at z0 or at z1, but we will certainly demand that they're closed curves at every stage. H of s comma a is equal to h of s comma b for all s in 0, 1. Again, let's draw a few pictures. Suppose our domain is something like this, and suppose this is our curve gamma 0, and this is our, maybe I shouldn't make it complicated. It can be as complicated as we want. If I make it complicated in this image, it will be difficult to draw the pictures. So let me keep a simple curve. Then at every stage there is a homotopy, means that at every stage we will be able to get hold of a closed curve like this, which slowly deforms to our curve gamma 1, and slowly it becomes more and more, maybe not that color, maybe violet, something like this, and so on. So this, at every stage there is a curve like this, maybe I should highlight now, and all these curves are based on some point. Oh, what are all these things? This is basically some gamma s0, this is some gamma s1 at some stage. I don't know which stage this will be capturing, but yeah, anyway, s2 and so on, where gamma, if gamma s of t is capturing the closed curve at the stage s, this image is representative of what is being written down here. So yet again, this is a closed curve slowly deforming to another closed curve. Remember that in this case, we are only demanding that at every stage the curve is a closed curve. Let's look at a very simple example of a homotopy between curves. So example, let's look at a convex domain. Let omega be a convex domain. What is the meaning of a convex domain? It means that if you have 2 points z0 and z1 in omega, then the line segment joining z0 and z1 is also contained in omega. I.e., if z0 comma z1 belongs to omega, then 1 minus t times z0 plus t times z1 belongs to omega for all t in closed interval 0, 1. This is what it means for a domain omega to be convex. Any 2 points. So this is for every pair of points z0 comma z1 in omega, the straight line segment is contained in omega. Okay, convex domains are special in the following sense. Suppose gamma 0 from AB to omega and gamma 1 from AB to omega be any 2 curves from z0 to z1. We are not putting any conditions on, oh, maybe I should mention something above here. So notice that to say that gamma 0 is homotopic to gamma 1 in either of these cases, be it in the first case where gamma 0 and gamma 1 are homotopic with fixed endpoints, or in the second case where it's homotopic as closed curves. In either of these cases, we are demanding something very powerful, the existence of a homotopy. What is a homotopy? Let me just write that down. In either cases, the map H is called a homotopy from gamma 0 to gamma 1. A homotopy from gamma 0 to gamma 1. So the demand that there exists a homotopy from gamma 0 to gamma 1 is quite special. There is absolutely no reason a priori to believe that there would be one such homotopy between a curve gamma 0 and gamma 1. It's quite a serious demand that there be such a map, capital H. This example tells us that convex domains are special in this sense. You take any gamma 0 from Z0 to Z1 and gamma 1 from Z0 to Z1, we will be able to construct one such homotopy all the time. Again, one more thing to note is that the homotopy that we have defined here, there is absolutely nothing that is being said about the uniqueness of such a homotopy. One could find gamma 0 and gamma 1 such that gamma 0 to gamma 1 can be homotoped by different homotopy maps H1 and H2 say. So there is nothing unique about the homotopy. This example, we are going to give one such explicit homotopy given curves gamma 0 and gamma 1. Define, so how do we go about doing that? Define capital H from 0, 1 cross AB into omega by using the convexity property of omega, H of S comma T. At the stage S, we would like to see what the map gamma S at T will be. That's just going to be equal to 1 minus S times gamma 0 of T plus S times gamma 1 of T. Geometrically, this is captured by a figure like this, where we start with convex domain. Suppose we have two curves from Z0 to Z1 and say this is gamma 0 of T. So this is say gamma 0 and this is say gamma 1. And suppose this is gamma 1 of T. We use the fact that the straight line joining gamma 0 of T and gamma 1 of T is contained in omega to define the homotopy. At stage S, it will be the point on this straight line. Gamma S of T will be on the straight line joining gamma 0 of T and gamma 1 of T by using the following relation here. Let us now explore some of the properties of the notion of homotopy that we just defined. The first one is that the relation of being homotopic is an equivalent relation. Let me write that down, the relation. So the properties will have the following setup all through. Let omega be an open subset and the relation of gamma 0 being homotopic to another curve gamma 1 with fixed endpoints. Is an equivalence relation. Let's give a proof of this. Let's first see that it's indeed reflexive. That means let gamma 0 be a map from AB into omega. Then we would like to show that gamma 0 is homotopic to itself. And consider the homotopy, consider the continuous map from 0, 1 cross AB into omega given by, at every stage, we have the map gamma 0 itself. This is equal to, this is defined to be gamma 0 of T. Then H is, I'll leave it to you to sit down and verify that this is indeed a continuous map. This is a continuous map, or I'll directly write it as a homotopy from gamma 0 to itself with fixed endpoints. Let us next prove that the property of being homotopic is symmetric. Let gamma 0 from AB to omega and gamma 1 from AB to omega are suppose two curves be such that gamma 0 is homotopic to gamma 1. Oh, maybe I shouldn't use the symbol yet. I'll start using the symbol of tilde to denote that they are indeed homotopic after we establish that it is indeed an equivalent solution. Such that gamma 0 is homotopic to gamma 1 with fixed endpoints. So when I say this, it means that the initial point of gamma 0 and gamma 1 is forced to be the same. The terminal point of gamma 0 and gamma 1 is also supposed to be the same. Otherwise, we cannot even talk about homotopy with fixed endpoints. We would like to see that gamma 1 is homotopic to gamma 0 with fixed endpoints. That's the goal, isn't it? What does it mean to say that gamma 0 is homotopic to gamma 1? That means that there exists a map capital H, a continuous map from 0, 1 cross AB into omega, which is a homotopy from gamma 0 to gamma 1. We'll now define a new map. Let's call it say H1 from 0, 1 cross AB into omega given by H1 of S comma T to be equal to H of 1 minus S comma T. We will go in the reverse order of these stages. At S is equal to 0, H1 of 0 comma T will just turn out to be equal to H of 1 comma T. And H of 1 comma H1 of 1 comma T will just turn out to be equal to H of 0 comma T. And it's an easy check for you to see that then H1 is a homotopy with fixed endpoints from gamma 1 to gamma 0. Therefore, the relation of gamma 0 being the relation of homotopy is a symmetric relation. And finally, let's establish that it is indeed transitive as well. Let gamma 0, gamma 1 and gamma 2 from AB to omega be such that gamma 0 is homotopic with fixed endpoints to gamma 1 and gamma 1 is homotopic with fixed endpoints to gamma 1, gamma 2. Gamma 0 is homotopic to gamma 1 and gamma 1 is homotopic to gamma 2. i.e., there exists homotopies H1 from 0, 1 cross AB into omega and H2 from 0, 1 cross AB into omega. There are two such maps capturing the homotopies between gamma 0 and gamma 1 and gamma 1 and gamma 2 respectively, such that H1 of 0 comma T is equal to gamma 0 of T, H1 of 1 comma T is equal to gamma 1 of T, and H2 of 0 comma T is equal to gamma 1 of T, H2 of 1 comma T is equal to gamma 2 of T. And the other condition of the initial point and the terminal point being Z0 and Z1 respectively are satisfied. I'll not write that down. We will now define a new map now, G, from say 0, 1 cross, or maybe let's call it H. We didn't use H in this. 0, 1 cross AB into omega given by H of S comma T. This we will go at twice the speed in each of the above homotopies. This is going to be h1 of 2s comma t, where s is between 0 and half, and when it is between half and 1, this is going to be h2 of ts minus 1 comma t, when this is the case. By a pasting lemma, it's very easy to check that h is indeed a continuous map, and the properties of h being a homotopy is satisfied because h1 and h2 are homotopies. Let me write that down. Then h is a homotopy. Oh, from where to where? So notice that h is indeed a homotopy from gamma 0 to gamma 2, because h of 0 comma t is h1 of 0 comma t, which is gamma 0 of t, and h of 1 comma t is going to be h2 of 1 comma t, which is gamma 2 of t. Homotopy with fixed endpoints. From gamma 0 to gamma 2. And with that, we establish that the property of homotopy is an equivalence relation. A very similar proof will tell us that the property of gamma 0 being homotopic to gamma 1 as closed curves is also an equivalence relation. A very similar proof. Tells us that the relation of homotopy as closed curves, this is also an equivalence relation. Let's see the second property. Suppose gamma 0 and gamma 1 are closed curves at some point z0. Gamma 0, gamma 1 be closed curves in omega at the point z0. Means that its initial point and the terminal point both are the same, and it's the point z0. Then gamma 0 is homotopic. Okay, maybe I should write, or I will not write that down explicitly. This symbol tilde will be used to denote that it is homotopic. We just proved that it is an equivalence relation. So this is justified symbol. Gamma 0 is homotopic to gamma 1 as closed curves. So I'll mention how, this way. If and only if there exists a closed curve gamma 2 at z0 such that gamma 0 is homotopic with fixed endpoints to a reparameterization of gamma 2 plus gamma 1 plus minus gamma 2, which is the reversal of gamma 2. So it will be a good idea, even in the previous case when we were establishing the equivalence relation here, it will be a good idea to actually draw the image of what we were doing. How did we define the map capital H, and see what we were doing. That will be actually a good way to understand the notion of homotopy. Suppose this is our given domain omega. Just to ensure that the idea of our domain being possibly far more complicated is captured, let me throw out a couple of disks. So what I am going to draw in yellow right now is the shaded region in yellow is our domain. The two disks are removed. So this is also possibly our given domain omega. Till now I have only been drawing some nice domains. It could get much worse than this as well, but it's good to keep in mind that we can have far worse domains in our applications. Alright, so what is the theorem telling us, or rather what is the property telling us? Suppose we start off with gamma 0 and gamma 1, which are closed curves at z0, then gamma 0 is homotopic to gamma 1 as closed curves if and only if there exists some other curve gamma 2 such that gamma 0 is homotopic with fixed endpoints to gamma 2 plus gamma 1 plus minus gamma 2. It means that suppose we have one such curve gamma say 0, and suppose we have another curve here which is say gamma 1, which is having the same fixed same initial point as gamma 1. That's something which has been put in the hypothesis. They are all based at z0 if you notice. So this is the point z0. Then what we demand is that we have a red curve of this type. So this is say like this, gamma 2, such that gamma 0 is homotopic to gamma 2 plus gamma 1 plus minus gamma 2. A reparameterization of it rather. Let's give a proof of this. The forward direction is possibly simpler, or maybe both are simple. Let's first prove the forward direction. What does the forward direction say? It says that if there exists a homotopy of closed curves from gamma 0 to gamma 1, then we will be able to get hold of one such gamma 2. So suppose capital H from 0 1 to omega be a homotopy of closed curves from gamma 0 to gamma 1. What does that mean? That means that before we draw what that means, let me give a new definition. Define gamma 2 from 0 1 to omega by gamma 2 of s to be equal to h of s comma a. The initial point or the initial and terminal point of the closed curve gamma s at every stage is being captured by gamma 2. So in particular, so this is say for example say gamma 2 of s0, then this is going to be the green is going to capture in some sense the homotopy that we are interested in, and the red is exactly being captured by gamma 2. That's defined here. Okay, so maybe I shouldn't draw those greens. Remove them. Okay, let us now try to establish that gamma 0 is homotopic to reparameterization of gamma 2 plus gamma 1 plus minus of gamma 2. In order to do that, we will ask with fixed endpoints. So we will define explicitly what our homotopy is, and the way to do that is by defining what at every stage s the homotopy is going to be. What we will be doing is, let me draw it in pictures to tell you what happens. The homotopy is going to be the following. At every stage s, I am going to capture it in green. We go along gamma 2 till the stage s, and we go along the homotopy gamma s, and then we come back. That's the curve that we will be capturing at the stage s. So this is say gamma s. This is going to be gamma 2 restricted to 0 comma s in the forward direction, and in the backward direction it will be minus of gamma 2 restricted to minus of s comma 0. Let me write that down. Define sigma s to be equal to gamma 2 restricted to 0 comma s plus gamma s plus gamma plus minus gamma 2 restricted to minus of s comma 0. So notice that minus of gamma 2 is a map from minus 1 comma 0, and the last part is captured by minus gamma 2 being restricted to minus s comma 0. So I'll urge you to sit down and check what sigma s is actually capturing. Notice that the way the concatenation is defined, so the plus is concatenation, the way concatenation is defined, sigma s is going to be from 0 to b minus a plus 2s, I guess. This is precisely where our map sigma s will be defined, and then we will reparameterize it. Reparameterize sigma s to obtain sigma tilde s from a, b to omega by a linear homeomorphism. Let me not write down explicitly what the homeomorphism is. It will be quite straightforward to write down what the linear homeomorphism from this domain to this domain will be, and then just compose it with sigma s to obtain sigma tilde s. All right. So now that we have what sigma tilde s is, let's just see what sigma 0 is, by the way. Before we go further, sigma 0 is just going to be gamma 2 restricted to 0 comma 0, which is just the point z0. Then gamma 0, then it goes along gamma 0, and then concatenated with minus of gamma 2 restricted to 0 comma 0. So this is going to be the constant curve concatenated with gamma 0, concatenated again with the constant curve. Hence, this is just going to be the gamma 0. And what is going to be sigma 1? Sigma 1 will be gamma 2 restricted to 0, 1, which is basically gamma 2. Therefore, it will be gamma 2 concatenated with SS1, so which is gamma 1, and then concatenated with minus of gamma 2. So indeed, if we define the map capital H of s comma t to be equal to sigma tilde s of t, then capital H is going to be homotopy from gamma 0 to a reparameterization of gamma 0 plus gamma 1, gamma 2 plus gamma 1 plus minus gamma 2. I'll just leave it to you to check that H is continuous. That H is a homotopy, that H satisfies the other conditions in a homotopy directly follows from the way we have defined sigma s. I'll leave it to you to check that H is a homotopy from gamma 0, homotopy with fixed endpoints. From gamma 0 to gamma 2 plus gamma to a reparameterization of gamma 2 plus gamma 1 plus minus gamma 2. Notice that we are freely using reparameterizations. One of the main reasons is because we are interested in the integral of a function, a continuous function, rather a holomorphic function on a closed curve, and we have already seen that this integral is invariant under a reparameterization of the curve. So we will freely move between reparameterizations because the integral anyway doesn't change. So if you sit down and check what the map H is, you will also be able to establish easily that it is continuous and see that it is indeed a homotopy with fixed endpoints. So that establishes one direction. The other direction is not very different. To prove the other direction, what is the other direction? Let's go back and see what it is. If gamma 0 is homotopic with fixed endpoints to a reparameterization of gamma 2 plus gamma 1 plus minus gamma 2, then we will show that gamma 0 is homotopic to gamma 1 as closed curves. So the first thing to note is that if gamma 0 is homotopic to gamma 2 plus gamma 1 plus minus gamma 2 with fixed endpoints, then in particular it is also homotopic as closed curves. And we just noticed in the first property that the property of being homotopic is an equivalence relation. By transitivity, hence, it is enough to show that gamma 2 plus gamma 1 plus minus gamma 2 or a reparameterization of that is homotopic to gamma 1. Let me write that down. To prove the converse, it is enough to check that gamma 2 is, or rather gamma 1 is homotopic as closed curves to gamma 2 plus gamma 1 plus minus gamma 2, or rather a reparameterization of this. By the equivalence, by using the equivalence, by using the transitivity relation, transitivity property of homotopy. Okay, let's give a homotopy of closed curves from gamma 1 to a reparameterization of gamma 2 plus gamma 1 plus minus gamma 2. How do we do that? Let's go back to the image we have drawn to capture what the homotopy we will be defining. What we can do is, we will start for every stage S, we will start at this stage, go along the, maybe a different color would be nice. Red is already taken. Let me take a blue. We can start at a point here, go along the curve here, traverse gamma 1 and come back. This is indeed a closed curve at every stage. And notice that after traversing through the entire curve, we will end up with gamma 2 plus gamma 1 plus minus gamma 2. So let's see what the curve is going to look like when we define it. Define sigma s to be equal to gamma 2 restricted to one minus s comma 1 plus gamma 1 plus the reversal of the above. That's going to be minus of gamma 2 restricted to minus of 1 comma s minus 1. And then you reparameterize it so that it is, let sigma tilde s from AB to omega be a reparameterization of sigma s through the linear homeomorphism that I was talking about earlier. Then what do we have? Then if we define H from 0 1 cross AB into omega by H of S comma T is equal to sigma tilde S of T, then it's again a simple check, a tedious but simple check to see that H is a homotopy of closed curves from gamma. Where does it start? At S is equal to 0, this is going to be equal to just the fixed point. So this is going to be from gamma 1 to a reparameterization of gamma 2 plus gamma 1 plus minus of gamma 2. So I'll just leave the details to you. Let's look at a few more properties. Another very important property is to observe that if you concatenate a curve gamma with its reversal, then it will be homotopic to a constant curve. Let me just write that down. Let gamma 0 from AB to omega be a curve from Z0 to Z1, and gamma 1 from AB to omega be the constant curve, gamma be such that gamma 1 of t is equal to Z0 for all t in AB. This is the constant curve at Z0. Then the property tells us that gamma 0 plus minus of gamma 0, the concatenation of this is homotopic to gamma 1. The proof is again quite straightforward. It's good to draw a picture. Suppose this is our curve gamma 1, or rather gamma 0. This is from Z0 to Z1. What we can do is at every stage, so this is going to be from here to say at stage S and then come back. Let me write that down and make things precise. For S greater than 1, let sigma S be defined to be gamma 1 restricted to 0 comma S plus concatenated with minus of gamma 1. Notice that minus of gamma 1 is from minus 1 comma 0. So this restricted to minus of S comma 0. This makes perfect sense. And sigma tilde of S be reparameterization of sigma S to AB. Define h of S comma t to be equal to sigma, okay, if S is greater than 1 and sigma tilde 0 of t to be equal to Z0 for all t in AB. And then we define h of S comma t to be equal to sigma S tilde of t. This is going to be a homotopy from a reparameter. So did I write that in the statement? So maybe I should correct the statement a bit. Then reparameterization of gamma 0 plus the reversal, that is homotopic to gamma 1. So notice that I didn't write anything about whether it's homotopic as fixed endpoints or whether it is homotopic as curves. Here it's going to be both. It's both homotopic as closed curves, and it is also homotopic with fixed endpoints with the homotopy which we have just defined. Then H is a homotopy. Okay, the homotopy is actually from gamma 1 to gamma 0. Notice that h of 0 comma t is actually gamma 1 of t, and that h of 1 comma t is actually a reparameterization. I'm a bit casual here. Reparameterization. H of 1 comma t is going to be a reparameterization of gamma 0 plus minus of gamma 0. And with that, we have established this property. Let me now give you a few more exercises for the remaining properties of homotopy. They are quite straightforward. So the first one is when gamma 0 from say AB, gamma 0 and gamma 0 tilde both be from AB to omega, and gamma 1 and gamma 2 from say CD, gamma 1 and gamma 1 tilde, let's put it that way, from CD to omega be such that gamma 0 is homotopic to gamma 1, or rather gamma 0 tilde, and gamma 1 is homotopic to gamma 1 tilde. Let me not mention whether this is homotopic with fixed endpoints or whether it is homotopic as closed curves. We'll fix one of them. Suppose this is homotopic with fixed endpoints, then gamma 0 plus gamma 1 is homotopic to gamma 0 tilde plus gamma 1 tilde. The concatenation of gamma 0 and gamma 1 will be then homotopic with fixed endpoints to gamma 0 tilde plus gamma 1 tilde. Had it been the case that gamma 0 is homotopic to gamma 0 tilde with as closed curves and gamma 1 is homotopic to gamma 1 tilde as closed curves, then gamma 0 plus gamma 1 will be homotopic to gamma 0 tilde plus gamma 1 tilde as closed curves. So long as we are not mixing these two notions, the equivalence relation makes perfect sense. Let me conclude by defining what is meant by null homotopic. Let gamma 0 from AB to omega be a closed curve. Then gamma 0 is said to be null homotopic, closed curve at Z0. Gamma 0 is null homotopic if gamma 0 is homotopic to the constant curve gamma 1 from AB to omega given by gamma 1 of t equal to Z0 as closed curves. So this is a homotopy as closed curves, and it's an immediate check for you to sit down and check that homotopy as closed curves here is the same as homotopy with fixed endpoints. By using the previous exercises, you can actually indeed establish this. I needn't have mentioned whether it was a homotopy with fixed endpoints or whether it was a homotopy as closed curves. Anyway, if we can get a homotopy such that the curve gamma 0 can be continuously deformed to a point, then we say that the curve gamma 0 is null homotopic. Now that we have discussed the machinery of homotopy in some detail, in the next lecture we will give a statement of the Cauchy's theorem, and we will prove a very special version of the Cauchy's theorem called the Goursat's theorem. Let me stop here.